consider the function f of x equals the natural log of x. And let's just look at the point where x equals 1. And we know that the natural log of 1 equals 0. And we could say, have a different function, g of x, and say that g of x equals 0. And if we were to look at the graph of these, the graph would look something like this. So there's f of x, here's g of x, and someone might think to themselves, well, okay, at that single point where x equals 1, g of x is a decent model for natural log of x, and at every other point it's a terrible model. Or at least right there it matches up. How could I make my model better? After a bit of thinking and just messing around, I go, well, if this thing were to have the same matchup at derivatives, that would mean that they're increasing or decreasing in the same way. And I noticed that the derivative of f prime of x at 1 is 1. And so if I want g of x to match up, I could change g of x so that not only does the function's value at 1 equals 0, but also the derivative would equal 0. So notice, if I change this to be x minus 1 instead of 0 plus x minus 1, when I plug 1 in to g of x, I will get 0. And g prime of x happens to equal 1. So now these two functions match up in two different ways. And so I can continue to graph and consider the relationship. Again, you could do this on your calculator to be a little more accurate, but just a quick sketch. ln of x is going to look something like that. X minus 1 is going to look something like that. You can see, at least for a little bit longer, maybe from here to there roughly, this is a much better match than just my original function. And we can keep going with that idea. And let's do it once more, but hopefully the idea has been illustrated. Well, what if these matched up at second derivatives as well? Well, the second derivative of 1 over x is negative 1 over x squared. And f double prime of 1 is negative 1. So now I'd like a function whose second derivative is going to equal negative 1. And I think about it just for a moment, maybe for a few moments, and I realized that if I added negative 1/2 times x minus 1 squared, when I plug 1 into the original, to g of x, I have a function who still equals 0. When I plug 1 into the derivative, I do get 1. And when I plug 1 into the second derivative of g, I get negative 1. And if I were to graph g of x now, this is what I'll find. Because now g of x is a quadratic, which means not only does it match up in terms of increasing and decreasing, but it also will match up in terms of concavity. So there's ln x looking something like this.